2-methylbutene reacts with concentrated sulfuric acid to form two different products. Outline a mechanism for this reaction. Show the formation of the major product. It's going to be difficult to explain this without showing it, so I'm going to do spoilers. So let's have a look. 2-methylbutene reacts with concentrated sulfuric acid. Butene, 2-methylbutene, 1 carbon, 2 carbon, 3 carbons, 4 carbons. So it's got 4 in a line. It's got a methyl group at carbon number 2, so this is carbon number 1, this is carbon number 2, and there's the methyl group. And it's bute, 4 carbons in a line with a 2-ene, a carbon-to-carbon double bond at carbon number 2. 1, 2, and there's the double bond. Sulfuric acid, well, in the mark scheme they've written it out like this. I sometimes refer it as HOSOH, so an S with an O and an H, and no and an H, and two S to O double bonds. But you could write it out like this as well if you wanted to. So I tend to show it again as HOSOH, and then the S having two oxygens, with S to oxygen having double bonds. But I don't suppose there's anything wrong with writing it out like this. An area of lots of electrons in the carbon-to-carbon double bond, so the electrons come from here, and the electrons in this second bond here join to the H. The reason that they go to the H and they bond to the H is because this is a polar bond, and the O is electronegative with a slight minus, a delta minus. This has got a slight delta plus. They've not drawn this on here. It would be better if they did, with a slight delta plus on this and a slight delta minus on here, but they're letting you get away without showing that this is a polar bond. And if the H is going to bond to one of these two carbons, then this bond needs to break and the electrons go onto the oxygen. So the question is now, where does this plus go? Or rather, where does the H go? In the major product, the H joins the carbon, bonds to the carbon that's got the most H's. So this carbon here, or this carbon here, wherever you want to say, this carbon here has got no H's joined to it. It's joined to a carbon, and it's joined to a carbon. It's joined to a carbon, it's joined to a carbon. It's got no H's joined to it, bonded to it, whereas this C here has got one H bonded to it. So the H bonds to this C, the carbon that's already got the most number of H's bonded to it. This hasn't got any H's, this has got one H. So it bonds to this carbon here. It doesn't really explain why, but at least means that you've got the H bonded to the correct carbon. And there's the H. The H there is bonded here onto this carbon. Now this carbon has now, since the H is bonded to the other carbon, hasn't got enough bonds. That means it's got a plus because it's lost a bond. Electrons are in bond, it's lost electrons, it lost minuses, it's become plus. And the electrons here have moved on to the oxygen, that's become minus. So this oxygen now is going to bond to this carbon. Remember, the arrow, however, doesn't come from the minus charge. The arrow comes from the lone pair of electrons. The pair of electrons in this bond have been deposited onto the O, and there they are, and the arrow comes from the O onto this C+, the carbon that's not got enough bonds and has got a plus. Then the minus and the plus cancel each other out, so this loses the minus and this gains the minus, the electrons that are moving, and it joins on in this fashion. So draw the structure of the minor product. Well, the minor product is where the H doesn't join the carbon that's got most hydrogens. So it doesn't join this carbon with most hydrogens. It joins to the carbon with the least hydrogens. That's very unlikely to happen, hence it being a minor product. It doesn't really happen very much, just a little tiny bit happens. So the H joins to this carbon here, and the OSO3H joins to this carbon here. In other words, these two are swapped over. The H is joined onto here, it would leave a plus here, and this would attack the plus and join onto here. These two are swapped the other way around. Why do these two products formed in different amounts? Well, let's have a look at this. A C with a plus is called a carbocation. Now, if you count the number of carbons off that C+, it will tell you whether it's primary, secondary or tertiary. So the C+, the carbocation, if it's got one carbon bonded to it, it's primary, two carbons bonded to it, it's tertiary, two carbons bonded to it, it's secondary, three carbons bonded to it, it's tertiary. So this is a tertiary carbocation. So tertiary carbocations are the most stable forms of carbocations. Next most stable are secondary, and the least stable are primary. So the fact that this has formed a tertiary carbocation with three carbons bonded to the C+ makes this very stable and makes this the major product, the reaction that's most likely to go ahead. If something's stable, then it's more likely to go ahead. If the H bonded to this H and this carbon here had the plus, if this carbon had the plus instead, as is the case in the minor product, this C had the plus, then this C would have only two carbons bonded to it. So your answer is that this tertiary carbocation is more stable than the secondary carbocation that would be formed in the minor product. There may be an extension mark at this point. It isn't in this question, but there might be an extension mark, say 3 marks. So why does this actually happen? Why is the tertiary carbocation more stable? And the answer is that a tertiary carbocation has methyl groups around it, or tends to have methyl groups around it, which repel electrons. The electrons reduce the size of the C+, by the way, and make the C+, the carbocation, more stable. But your answer is, if it said, why is a tertiary carbocation more stable than a secondary carbocation, or why is a secondary carbocation more stable than a primary carbocation, it's because the methyl groups surrounding the tertiary carbocation repel electrons.